Is it okay to start over here? Need a minute? Okay, I'll start slowly. We have some folks in the room that are joining on the French channel as well. So welcome everybody. We're really happy to be joined today by our three colleagues at DLR who I'll let introduce themselves. They'll be presenting the final results and facilitating a discussion about the research that they've done for us in the Lake Kivu and Ruzizi River Basin as part of our GIZ project, which is a partnership with Abekir. And so we'll be getting the final results and then discussing, and particularly I'd be interested for us to all discuss next steps about what we think we can do with this data and information moving forward in the basin. We probably don't want to do entire introductions because there's a lot of us on the call and we're starting a bit late. So what I'll ask is for those of you participating, if you could just write in the chat your name and the institution you work with, and we can all see where everyone's from, but we'll save time that way. In the room, I'll write in the chat for everybody. So a few of us are gathered here in Kigali because we're having other meetings with Abekir and Rwandan Water Board. So I'll write for the chat who all is in here. But then everyone else on the French and English channel, please write in the chat and we'll share. I believe we're saving most discussion topics for the end, Felix, or would you like to take questions during as well?
I think it's better to have them in the end. Maybe if there are questions, they can be posted in the chat. And maybe my colleagues can also answer some of them in the chat, but due to the fact that we have the two channels, I think it's easier to have the discussion in the end.
Okay. So I'll try to, as a reminder, to make sure we have interpretation. So to speak slowly so that the interpreters have time to translate in the French channel. So I will also slow my pace. And yeah, if there's clarification questions, feel free to post them in the chat during the presentation. And then we'll save discussion questions for the end. Like Stephanie said, it'll be easier for the interpreters. With that, I'll pass it over to our colleagues at DLR. And if anyone at any time has any technical challenges, please also post in the chat. We have two of our colleagues at GIZ. We have two colleagues at GIZ who can also help. And Steffi will be posting the questions we have or the introductions we get on the French into the English and vice versa, so that we can all see the chat, even though we're on two separate channels. And so with that, I'll pass it to DLR. As a reminder to everybody, please make sure you're muted so we minimize any background noise if you're not speaking. Thank you.
Yeah, thank you, Christine, for the introduction. Yeah, we have three people from DLR today. I don't know, do you want to introduce yourselves, or I can also say some words? And
maybe briefly, yes.
Yeah, okay, then you can start, Felix.
Okay, so Muraho from Munich. It's a pity that we can't be in Kigali today with you to discuss. I would have enjoyed to coming back to Kigali also to visit some friends. I learned in several projects there. I'm happy that we have this meeting today to introduce some of our results, most of which Steffi was responsible for. So she did most of the work. And for us, it's a super interesting scientific exercise to look into the Earth observation data and to see how it's possible to complement what has been done in the already existing study that was also supervised by Abekir, and that focuses then what Earth observation can add to the results of erosion risk. And also, of course, what's also interesting, and I'm glad that Xuan is also here then, to see how we can model from existing data. And here we have a great data set that enables this modeling of data of urban growth for the future. Yeah, we are a small team at the German Aerospace Centre. I have with another colleague, Juliana, the lead of this team, and focusing on water-related topics, so that fits quite well. And yeah, and I wanted to brief, so therefore I pass directly. I think better first to Xian, and then Steffi can take over.
Hello, everyone. So it is also my pleasure today to join this meeting. And I am Zhiyuan Wang. I'm also working in the team of Coast River Basin from Earth Observation Center of DAR. So my job in this project is basically using our existing Earth observation data for the urban extension to simulate the future urban growth of our study area. Because we know the urban area is actually very important because they change also the ceiling factors of the surface. So therefore, in this project, we thought it would also be very interesting to also simulate the urban areas in our study area. And in the later presentation, I will show you or introduce you some details of our implementations and also the parts of the results. And yeah, thank you, and pass it to Steffi, please.
Yeah, thank you, you two, for your introduction. I can also agree with Felix. It's really a pleasure for me to be here today, and that so many people of so many places joined, and that we can have this meeting together. And also, it was a really nice project for me because it was an area I have not worked in before, and I learned a lot about the area. Also, looked at a lot of pictures of the area, and really enjoyed my work here. And also from a scientific point of view, it was really nice to combine different Earth observation products and to have these nice results in the end. So I think we can directly start with the presentation then. Moment, just skip here. Okay. I start with a little outline, and first I want to draw your attention to this picture on the right, which I took from National Geographic, and this really is, for us, it was, as I said, really nice to work with data of the area, but also on the other hand, it was a bit sad that we couldn't really visit the area and meet you guys in person. And during my work, or especially in the beginning, I looked at a lot of Google Earth, a lot of photographs, just to get a feeling of the area. And it's really, as you can see from the pictures, and you know this, it's a really beautiful area. And yeah, maybe one day we can all meet together, or we can visit the area and see really how it looks and get also another feeling for it, because our work always comes from a satellite perspective, which is quite far away, and on the other side is quite close to the ground. But yeah, it's always nice to really see the area in person. So now I give you a little outline on my talk today. Will not go too much into detail because we will see all of this later, of course. First, I will give a little overview on the project. There's noise background. Do you hear me still?
Yeah, there's just a lot of background noise.
Okay, yeah.
Okay, it's done.
Oh, yeah. Okay, so first I will give you a little overview on the project, just briefly. Then I will show you the workflow and the work packages of our scientific work, and then I will introduce you to the 4 work packages that focus on the scientific work of this project, and in the end I will give a summary, and then we can have a discussion on anything. But as we said, you can post whenever you have questions. You can also post them in the chat so we don't forget about them, and also my colleagues can start to answer them. I really try to speak slower now because I know we have the translation into French, but yeah, try my best. So a little outline on the project. So on the left side, you see The area that we were focused on, the study area of Lake Kivu and the Ruzizi Basin. So we have the big Lake Kivu in the northern part, and then we have the Ruzizi Plain in the southern part. This figure on the left is actually taken from your baseline study that you performed, and yeah, it's a nice overview of the area, and the work we have done wants to supplement and complement the work of the baseline study to see what we can do, how we can quantify erosion risk in the area using Earth observation data, so from a satellite perspective. You have performed a Russell simulation in the baseline study, which also quantifies the erosion risk in the area, so we have a nice way to compare the different approaches. The parameters that we considered are the precipitation, the vegetation dynamics, also the land use, and then Jian will present the results on urbanization, on the urbanization development in the area and in the past, but also will show some simulations of the urbanization in the future. So the project time frame was 6 months, starting in July last year and then ended in the end of December. Yeah, we are glad that we can now have this, show you these results of this half a year work. The results are summarized in a report which you already received this week, and there will also be a data package which will be made available. There are some intermediate results and some really geodata for you if you want to take a closer look. I have a download link. I think we can share it maybe in the end of the presentation. Maybe in the chat, or we can discuss later how we share the link exactly. Okay, so here is the outline of the research project, which was subdivided into 5 work packages. And the 4 work packages are the scientific work with the data, and I will present you the results of these 4 work packages today. So work package 1 focuses on the vegetation dynamics on a long-term scale, but also on a seasonal scale, to see when we have low vegetation and dense vegetation, which has a strong effect on erosion. The work package 2 then focuses on the second important parameter for erosion, which is of course the precipitation, because precipitation is the reason why we have the washout of sediments. And these 2 work packages, the vegetation and the precipitation, are then combined into an erosion risk parameter. In work package 3, we then look at the lake turbidity of Lake Kivu, and we want to see if we can see a change in turbidity due to erosion. And this would be a way to validate our erosion risk index that we defined. So to see if we really got erosion in the turbidity. Then, as I said, we also look at the urban growth in the area, not in the full area, but in 2 cities in the area, the city of Bukavu and the city of Goma, which are in the north and in the south of Lake Kivu. And Jian performed some model simulations to see how the urban area changes until the year 2050. So we start with work package 1, the analysis of vegetation dynamics. For this, we decided to use MODIS data. Why did we decide that? Because the MODIS satellite system, it consists of 2 satellites, the MODIS Terra and MODIS Aqua satellites. It covers a really long time range because there's data available already from the year 2000. The 2 satellites, they measure reflectance data in 36 wavelength ranges, so 36 bands. And NASA delivers very nice products derived from these 2 satellites. So you can download ready-to-use data from different platforms, but there's one data download link given here in the presentation. So here you can get MODIS data of the last 21 years already. So this is quite nice. The MODIS data comes in a specific grid. So this is a MODIS projection where you can see every grid that's on this figure here is one image tile. So one image that you can download. And as you can see, the yellow frame shows the location of Lake Kivu, and the whole study area is covered with one image tile. So this was quite convenient. We could download this image tile for the 20 years. And there's already a ready-to-use MODIS Ndvi product available that is provided by NASA that we use for the analysis. The product is called MOD 13Q1 for the Terra satellite and MYD 13Q1 for the Aqua satellite. And this is the highest resolution Ndvi product that is available from MODIS satellites. It has a temporal resolution of 16 days and a spatial resolution of 250 meters. On the right side of this slide, you see the workflow that we performed with the MODIS data. So of course, first we downloaded the MODIS data for the 20 years, starting from 2001 to 2020. The data comes with a quality layer, and this quality layer includes information on the location of clouds and low quality pixels. Also, you get information on snow, but that was not so much of a problem in this area. So we flagged the clouds out of the data and also flagged out low quality pixels within the study area. So then we get the clear only Ndvi product for each pixel without any disturbances. These products then, so we have every 16 days one image of the area, which is cloud flagged. From this data, monthly medians were calculated to get a more generalized overview. And these monthly medians were then aggregated to a 0.025 degrees hexagonal grid, so that we can more look at the data in a more generalized way. And then, yeah?
0.025 means how many meters?
That is around, Felix, do you know? We can't hear you, John.
I'll do the calculations. It's fine, thanks.
You're muted, Felix.
That's fine, it's fine. Let's proceed. I'll do the calculations. It's, I think 1 degree is 130 kilometers. And then we'll just do the calculation. Thanks.
Okay, perfect. Okay, so here on the right side, you can also see the grids. You see it's quite small, so that you can get a feeling for it. Yeah, so what we first looked at the long-term vegetation changes. And here on this slide, in the first row of the figure, you see the median of 5 years of the Ndvi. The greener the color, the denser and greener the vegetation is, and the more brown the color, the less dense and less green the vegetation is, or there's even no vegetation there. So you see the date ranges from P1 to P4. P1 covers the years 2001 to 2005, P2 2006 to 2010, until P4 from 2016 to 2020. So this allows us to look at the changes in vegetation over long term, over 20 years. And as you can see from this first row, we have this very high vegetation, or very dense vegetation here in the southwest of the area, where there are some preservation areas, the Ndvi forest and the Kibera National Park. And there we see throughout the study that there's very dense vegetation all year round, because it's a forested area and it's also a mountainous area. We also see that in the Ruzizi plain here in the southern part, there is rather low vegetation compared to this, because here we have land use, and we will look at these factors later on as well, what provokes this lower vegetation cover here. To see how really the vegetation cover changed over time, we also performed a difference plot. So in the second row of this figure, we see the difference in Ndvi median from a period to its previous period. For example, here in the lower left, we see the changes from P1 to P2 by just calculating a difference of P2 minus P1. So this shows us the changes in vegetation, and if the color is red, then it's a decrease in precipitation in vegetation. If the color is green, it's an increase in vegetation. And what you see here is that we have a decrease in vegetation north of Lake Kivu, where the city of Goma is located. Especially from P1 to P2, we see this very strong decrease here in the very northern part of the study area. And actually, I found that this is probably due to volcanic eruptions that took place. I think 2006 there was one, but also a bit later, 2010, that really destroyed some vegetation here in the area. And apart from this, we also see the loss in vegetation, probably due to urban growth in the area around the city of Goma. There's also some decrease from P2 to P3 here at the buffer zone of the national park area. And this may also be due to forest clearing. There was actually a study I found which also found that there was forest clearing at this time period at the buffer zone of the national park. But when we look at P3 to P4, so the changes from 2015 to 2020, we also see an increase of vegetation in the area, maybe due to afforestation in the area. So these changes show us the long-term changes of vegetation cover, but they have not so much to do with the erosion, because erosion takes place whenever there's open soil. It doesn't need a long-term change to provoke erosion. This is why we also looked at the seasonal changes, and this is now the part of the analysis of vegetation dynamics, which really goes into our estimation of erosion risk. So for the years 2016 to 2020, we calculated seasonal medians of vegetation for the wet season and the dry season. Dry season for us was June, July, and August, when we really have low precipitation in the area, while wet season was then the rest of the years. And here you see the median for these 5 years for wet and dry season. So on the right side, where we have the dry season, you see that there's in the Ruzizi plain, there's really low Ndvi for this time of the year, which shows us that at this time of the year, there is not so much vegetation cover in the area. Also, we have low vegetation cover here in this northern part of the study area, where we have the slopes of the mountains, of the volcanoes here, where also there's a lot of agriculture found. Again, we see in the national parks and in these preservation areas, we have year-round, also in dry season, we have very dense vegetation cover. So this is really nice that this also lives through the dry season, that also through the dry season we have very dense and stable vegetation cover. One thing I want to draw your attention to is this low vegetation, or this low Ndvi along the coast of Lake Kivu. This is not necessarily due to low vegetation cover. It may also be due to mixed pixels that are only partly covered by vegetation or by ground, but also partly by lake water. And then due to this mixture, there may be a resulting low NDVI, but it can also be due to urbanization along the coast, and this may also lead to low NDVI values here. It can also be due to the movement of the coastline of the lake. This analysis, the seasonal medians, they were all calculated for every year from 2016 to 2020 to see the differences between the year, the interannual and interannual differences in vegetation cover. And what you can see here is that the changes from wet to dry season are not always the same or not as strong for every year. For example, we see 2016 there was quite low NDVI during dry season in the Ruzizi plain, while for example 2008 it's not every year is the same in vegetation cover, which of course also affects the erosion risk from year to year. So it's important to look not at the whole period at once, but also to make a difference between the different years. And a second parameter we wanted to look at, not only the vegetation cover, but also the land use that is connected to this vegetation cover. For this, the next slide shows you an overview. So this shows you the land cover in the area. It's based on the ESA World Cover 2020 map, which was published last year. So it's a very recent, very high resolution land cover information based on Sentinel-1 and Sentinel-2 satellites. It has a 10-meter resolution, which is really high and really good. It has 10 land cover classes, which you can see in the legend next to the figure. And with this data, we could take a look what land covers lead to low NDVI values. So if you now look at the map of land covers, you see that this brown color, which indicates cropland, is mainly found along the Ruzizi River in the Ruzizi Basin, also south of Lake Kivu and also around of Lake Kivu. And in the southern slope here in the north of this mountain, there's also a lot of cropland found. Apart from this, there's a lot of grassland found in the Ruzizi plain and also around Lake Kivu. And what stands out again is this very dense tree cover where the national parks are found. So,
Quick question.
yeah.
You said that the land cover comes from ESA 2020.
Mm-hmm.
But in the pie charts, you have dry and wet, which I think is not from ESA. How is it?
Which?
How did you come to that? And maybe we can't have a land cover. Okay, I presume the land cover is uniform across the year. Along, what do you think?
I didn't understand the first part of the question.
The first question is that is the pie charts of land cover. Is it coming from ESA or is it an analysis?
Yeah, that's an analysis. I will come to that now. Yeah, as you said, yeah, that's true. So we don't have a land cover that's changing in time. We just have this one map based on the data of 1 year. So it's not changing over time, but the land cover, it will also not change that quickly. So cropland is probably cropland for longer than a few months. So it would be okay to use this data for a full year or even for the 5 years time frame, because the land cover doesn't change that quickly. But now I come to the right side, and maybe then your question will be answered. So what I showed you a few slides before was the NDVI median for the study area in wet and dry season. And the pie charts now show what land cover is found for hexagons with an Ndvi below 0.5, so with a low Ndvi. And this is what is shown here on the right. So for wet season, you remember that there was not so many pixels that had a very low Ndvi value. And then we took a look at what land covers are found for these hexagons. And the most prominent land cover for low Ndvi values was the water class, so water bodies. And when you remember what I said before, that there are these mixed pixels around Lake Kivu, this leads to the fact that we have these water pixels as lowest Ndvi value during wet season. The second class during wet season is grassland with 22%, which is found also in large areas of the study area. Then during dry season, the picture changes a lot. Water is not that prominent feature anymore, but we have the most hexagons that have a low Ndvi values have grassland as their main land class. And on the second class, we have cropland. So cropland is during dry season an important land cover, which leads to very low Ndvi values. So this means that the agricultural practices or the harvesting of crops before the dry season leads to a lot of bare soil, open soil, and this leads to very low Ndvi values in the study area. Also, of course, the grassland, because the grass dries out during dry season and then doesn't give us this high Ndvi values anymore. So it's different from trees, what you see during wet and dry season. Trees always lead to high Ndvi values for both seasons and throughout the year. So now we analyzed the vegetation dynamics and also the land cover in the area. And when you remember what I said in the beginning, the second important factor, of course, you know, this is the precipitation. So now we start with the work package 2, the analysis of precipitation. So to analyze the precipitation pattern, we used CHIRPS data. CHIRPS stands for Climate Hazards Group Infrared Precipitation with Station Data. And as the name already says, it incorporates satellite imagery and together with in situ station data. The dataset is quite good in quite a long time, covers a long time range of now more than 40 years already. And it covers all longitudes, or latitudes, it must say, from 50 degrees north to 50 degrees south. So of course also our study area is covered by this dataset. For our analysis, we used the daily temporal resolution, so we got one product every day, and we again aggregated this data to a 0.025 hexagonal grid. So this is then the same grid as for the vegetation, so we can combine this data in a good way. These plots here, they show the mean monthly precipitation sum per hexagon. So for each month during wet season, the mean is calculated, and for each month of the dry season. What stands out and what is quite clear is that during wet season we have a lot more precipitation than during dry season. We have some hotspots during wet season as well. You see that there's a connection of precipitation to the topography. So where we have high mountain ranges, we also have stronger precipitation during wet season, but also during dry season. And also, especially during dry season, we have very low precipitation values for the Ruzizi plain, which during dry season go down to almost zero. Also during wet season, there is not so much precipitation in this area. Now we wanted to analyze not only the precipitation, but also we wanted to find out when are extreme precipitation events, because extreme precipitation events, they are able to wash out a large amount of sediments, and they can also only last like a few hours or a day or maybe 2 days. And we have wanted to identify these extreme events that are short in time and maybe also small in scale, in spatial scale, but that can provoke large precipitation events. For this, we had to define a threshold. This threshold gives the value of each hexagon for which the precipitation can be classified as extreme event. And for this, we determined for each hexagon the 1% strongest precipitation events that took place within the hexagon. So the figures on the right basically show the value that for which the daily precipitation, if the daily precipitation exceeds this value, this day is considered as a day with extreme precipitation events. And these numbers also, of course, change over the study area and also for the seasons. So during dry season, not such strong precipitation events are needed so that we can classify them as extreme events. And then we used every daily data set in the study area and counted the number of strong precipitation or extreme precipitation events for each hexagon. So this sounds maybe now a bit confusing, but maybe it becomes more clear when we just look at the result of this analysis. So here we see the year 2016, and we see every month of this year and the number for each hexagon, the number of extreme events. So for example, in August, we see in this southern part of the study area, we have some hexagons where we have up to 6 extreme events. And also, of course, we have a large number of hexagons also here in the northern part where we have no extreme event at all. And this pattern of spatial distribution of extreme events, this analysis was performed for each year from 2016 to 2020. And the numbers were counted for every month. But we do not get a pattern that we can say, okay, every August we have very strong precipitation events, or in July there's nothing. But we can see a pattern that in the earlier months of the year, in April or May, we often have a peak. For example, here in May, we have a small peak. Then there is often a peak in August in the data, and there's often towards the end, there's a third peak. For example, here in December, we do have a little peak, but in other years, we see this a bit more extreme. But we cannot say that one particular month is more threatened than other months. So now in the next step, we combine the vegetation analysis and the precipitation extreme events to get an erosion risk index. So for this, we just more or less multiplied the Ndvi with the number of extreme precipitation events for each month. Of course, we couldn't just do a straightforward multiplication. We used this formula that you can see in the lower part of the slide. So this just means the Ndvi range was normalized to values between 0 and 1 and then turned around so that high Ndvi values lead to a low factor and low Ndvi values lead to a very high factor close to 1. So these two parameters are then multiplied and the result looks like this. So we get a monthly erosion risk. This is an example for the year 2016. We get a monthly erosion risk for the full study area. You see that the example of August here, where we had a lot of extreme events in the southern part of the study area multiplied by the Ndvi, which is very low during that dry season time of the year in the same area leads to a very high erosion risk here in August in the southern part. But we also have other months where we do have increased erosion risk around the lake and in the southern lake and also here in the Ruzizi plain. But we also have months like in 2016, July and October, where there was only very low erosion risk found. To get you a better estimate or overview on these results, because I mean the monthly visualization is important, but it is also a bit difficult to grasp for us, so to understand what really is now the result of this analysis, I summarized the results of the 5 years analysis, and what came out is this figure on the right. So on this slide, you have a comparison between our results of the years 2016 to 2020 with the results of the Russell simulations. And on the left side, I've taken the figure from the baseline study of the Russell simulations, and next to it, I put the sum of erosion risks from our analysis of the 5 years from 2016 to 2020. So here on the right side in the figure B, you see the overall erosion risk derived from our analysis. And what you can see is that there is increased erosion risk in the Ruzizi plain, but also around Lake Kivu, especially north of Lake Kivu, but also on the eastern coast, there is increased erosion risk. Again, we see that there's very low erosion risk for the national parks and the forested area in the southeast. This is due to the very high Ndvi values throughout the year. So the erosion risk index is never really high for this area. And then when we compare our results to the Russell simulations, we see that there are a lot of similarities. So we see that both approaches get increased erosion risk north of the lake, also in the Ruzizi plain, also east of the lake. But what we also see is that the approaches lead to, in some places, especially in the southern part, lead to a little shifted erosion risk. So our approach identifies erosion risk a bit more to the west compared to the Russell simulations. This is, of course, due to the completely different database, but I think it's a really good result for this, that we use completely different approaches. So what we can say is that both approaches lead to similar results and they can be used complementary. So we can use the results of both approaches and get valuable information out of it. So we now come to the third work package, which analyzes the turbidity of Lake Kivu. And when you remember what I said in the beginning, we wanted to use the turbidity of the lake to have a validation of our erosion risk analysis, to have because we wanted to see if we can really measure increased turbidity when we identified increased erosion risk. For this, we used the turbidity product of the Copernicus Global Land Service and took the data also from 2016 to 2020, which is based on the Sentinel-3 satellite. So we downloaded all the data for these 5 years in a 10 days spatial resolution, so one image every 10 days and 300 meters temporal resolution and the 300 meters spatial resolution. And on the right side, we see the annual or the monthly turbidity of Lake Kivu, and we see that there is an increased turbidity in March here and also in April, and then towards the end of the year from October to December, and there is really low turbidity for July and August for the lake. This is also visible not only for 2017, but also for the other years. So now I took one example of our erosion risk analysis to compare with the turbidity. This is May 2017. And what you can see is that the erosion risk identifies very strong, a very high erosion risk around the lake area. So we even have this dark red, purple color here. So this means very high erosion risk. And then when we look at the right side, at the turbidity, we see that there is in the most part of the lake, so in the center of the lake, there is not really an increased turbidity. But when we look at the edges of the lake, so at the coast, and especially at the river deltas that flow into Lake Kivu, we see a very high turbidity here. So this may be due to erosion. This is more like a qualitative analysis. And to get this more quantified, we also performed a quantitative analysis in the comparison of erosion risk and turbidity, which is shown on this slide. So the quantitative comparison compares the erosion risk in the basins around Lake Kivu to the turbidity close to the coast of these basins. So for example, we have the two basins in the north that are indicated in green color, and we used of each month, we calculated the mean erosion risk for these two basins in the north and compared it to the mean turbidity of the first 100 first kilometer along the coast of these basins. So we used only the turbidity along this area and compared it to the mean erosion risk for the two basins here. And this we also did for west and east and southern basins. And on the right side, we have then this scatter plot. On the x-axis, there is the erosion risk. On the y-axis, there's the turbidity. And what we would have expected was that we get high lake turbidity values for high erosion risk values. And what you can see from the figure is that there's not such a clear connection visible, but at least for most areas, we do not get very high erosion risk and at the same time very low lake turbidity. So this is maybe a small gain in this analysis, but also we must say that the connection is not that strong. The reasons for this low connection or this low connection between the two parameters might be that even though we identified increased erosion risk for the basins, maybe erosion didn't take place. So we don't know if erosion really took place. So this is one reason. Also, the turbidity has a quite high spatial resolution of 300 meters, and also the monthly medians lead to a quite low temporal resolution, and this might lead to a dilution of the results. So maybe we have the river deltas that have very increased turbidity due to erosion, but due to the monthly medians or monthly means, this small scale increased erosion is not coming out into the results. Also, the turbidity is a factor that is not only influenced by erosion, but by many other factors, for example, human activity, but especially by wind and waves that result from the wind that can lead to increased turbidity, although there was no erosion. So it's not the only erosion, it's not the only factor that increases the turbidity. But we think that a closer look at the river delta, so really only the area that is very close to where the river flows into the lake, an analysis of this part and also maybe a higher resolution product could lead to more supportive results here. So on our next slide, we start with work package 4, the simulation of urban growth performed by the Sleuth model. And I would hand over to my colleague Xian now. Maybe I can share the presentation, Xian, and you tell me when to click.
You can do the click, and I will just do the presentation.
Yeah.
Thank you very much, Steffi. as my colleague Steffi already said, that the urban growth is also a very important factor also for analysis of erosions, because the urban development actually changes the silt surface of our study areas. So it would be also interesting to get a closer look to see how actually the urban or the city develops themselves in the future. So here we selected two biggest city agglomeration around Lake Kivu. So namely the city agglomeration of Goma and the city agglomeration of Bukavu. By saying the city agglomeration is because it doesn't only include the major city of Goma, but also the other cities around this region. So together we selected these two city agglomerations. So next slide, please. And here I would like to give you a short introduction of the Sleuth model. So the Sleuth is a name that consists of the model's input parameters. So they are namely the slope, the land use, the exclusion, also they're called excluded areas or excluded regions, and urban extent, transportation, and as well as the hillshade. And this model consists of two cellular automata models. One is for the urban growth simulation, the other is for land use changes. And for our study here, we only used the first one, which is for the urban growth model. And this model is developed by Clark cellular automata model based on this one. And it is widely used for future urban growth development. And the basic assumption of this model is that it assumes that every city has its own DNA. That is to say, the city will develop in the future as they used to grow in the past. So we basically analyze the historical development of this city and to use it to predict or to simulate the future urban growth. And for these simulation, we mainly use the world settlement footprint from DRR, which is a really good Earth observation data product from DRR. And we mainly use this to generate historical urban extent and to do this urban simulation. Next slide, please. And in this slide, you can have a further look of what or how the world settlement footprint actually look like. So the world settlement footprint is, as I said, a satellite-based imagery product produced by DRR, and it provides or outlines the global settlement coverage or extent at a very high resolution. It provides two resolutions. One is in 10 meters, the other is in the resolution of 30 meters. And it is based on an annual observations. That is to say, we can have urban extent for every year from 1985 to 2015. And in these two figures, you can see, in these two imageries, you can see that pixels are having different colors, and the different colors indicates the year that the pixel has been urbanized. And next slide, please. And aside from the world settlement footprint, we also used other input parameters. So we used a water mask and a nature preserved mask for generating our excluded layers. The excluded areas means that urban cannot be developed in the future. So namely, we used water because the water areas will resist urban growth, as well as we used nature preserved area. And nature preserved area was obtained from the world database of the predicted areas. And for the traffic network, we use the road network obtained from the Global Road Inventory Project, so the GRIP data. And for the slope and hillshade, we generated it from the Copernicus digital elevation model. So next, please. So as a result, the Sleuth generate the probability of future urbanization for each pixel. So in these two figures, here you can see already that these color-coded maps illustrate the probability of urbanization generally from generated from 2015 to 2050. The red color illustrates a high probability of urbanization in the future, and the green color means a really low probability for the future urban development in these two regions. And this is the result of city, sorry, this is the result of city agglomeration of Goma. And as you can see that we simulated these results based on two countries by considering the different situations or from two countries. And next slide, please. And as well as this one. So this slide shows the future urban growth of the agglomeration of
I'm very
Bukavu.
sorry. Can I just quickly interrupt? We have an
Yes.
interpretation service problem because I think, Laurent, you're muted in the French channel. Okay, it works again. I'm really sorry. You can continue.
No problem. Yes, as you can see in this slide, we show you the simulated result of the probability of urbanization from 2015 to 2050. So again, different colors illustrate the different probability of future urbanization in this region. And comparing to the last slide, we can see that this region has a relatively low probability, and we assume it is because of the terrain. Like this region, it is really located in a mountainous region, and due to a steeper slope, so urban cannot develop that fast in the future. And next slide, please. So by selecting a threshold of the probability, in the end, we generate the future urban simulation, future urban development for these two city agglomerations. As you can see that we have a relatively fast development, city development, urban development in the city agglomeration of Goma, and relatively slow city development for the city agglomeration of Bukavu. The differences would be because of the terrain and as well as probably some other factors. And as you can see clearly that the yellow colored indicates the future development. So yeah, that's what we've done for the future city simulation, development simulation from 2015 to 2050. And this result will provide a roughly look and also some extra information if we want to enter or do some further analysis for the future erosion analysis and so on. And yeah, that's basically all the information from this part. I will handle this presentation back to Steffi, please.
Thank you, Shiyan, for showing your really nice results. So this was more or less the end of the talk. I will now give you a summary of all the information that I gave you. Can you hear me?
Sorry, Stephanie. Really quickly, Musana has to leave, but he has one question on what was just presented.
Yeah, sure.
Very quickly, I think there's some analysis showing in the different lakes, like in Kenya, how the point source and the non-point source affect the water quality. Maybe those reference can help you interpret the response of the catchment to the quality of water.
Mm-hmm.
And then we also think that the adding topography in the catchment characteristic could help in improving the interpretation, or either the model or the interpretation of the response. It's something you can explore in the quantitative analysis, or if you want to improve the index. Another quick one is that the area you're just showing in the slide here, where we have the yellow patches, is not in Congo, it's in Rwanda. So when we say Goma agglomeration, we should call it probably Goma Gisenyi agglomeration or Goma River agglomeration, because the result shows that more increase in agglomeration in Rwanda. And when we say it's Goma, it can be misleading for colleagues.
Yeah. Yes, you're absolutely right. So first, in the beginning, we wanted to simulate the urban growth of the city of Goma, but then we realized that the city of Goma is a small part of this agglomeration of urbanized area. So then we extended the area covering also Rwandan cities, but then we called it the city agglomeration of Goma. But of course, there are also a lot of other places that are not even in the same country that are within this agglomeration. So maybe we should adapt the naming of this area. Yeah, you're right. Yeah, thank you for your advices also with the slopes. I think this could also really be an asset to our analysis and improve the results or get us a bit better estimations of the risk parameters.
Yeah, may I hear? There were also some questions in the chat, and one also was related with the slopes. I think that was something that we discussed in the beginning. And of course, slope is absolutely one of the most important parameters for erosion risk. But in this case, since we just wanted to complement the existing analysis of the Russell model that was presented in the ABAC report, we did not use the slope because it was already used in there. And by using the slope again, we would have used it redundantly. And that makes it more complicated to combine both results. And that's actually something that would be actually the next step to combine both results and then to make an interpretation of that. So therefore, we did not use the slope. But of course, I totally agree that slope is the first thing you think of discussing erosion, besides of precipitation, of course.
Yeah. So I would also say that the really special thing about this analysis is that we have two approaches that have completely different data sets that do not overlap at all, and we get similar results in the end. So this is why it's really, really cool that we do this together, that you have done your Russell simulations and now we do the Earth observation part and compare these results. Yeah, this is a good, or are your questions answered, or is there more to discuss on that?
We're good.
Okay, then I will continue with the summary. Yeah, I showed you the long-term vegetation analysis in the beginning, which shows the changes in vegetation for some areas. There are losses in vegetation cover or forest cover due to urban growth, due to volcanic activity, due to agricultural activities, also due to forest clearing, but also we see that there's afforestation, especially in national parks. So there's not, you cannot say there's really a strong loss in vegetation cover over a large area in within the time frame of the analyzed, within the analyzed time frame. There's also areas where we have a very stable vegetation cover over the full time period, especially in the forested mountainous areas. The seasonal dynamics of vegetation show that there are strong changes in the density of vegetation cover and in the greenness of vegetation cover within each year. So from wet to dry season, we have a strong loss in vegetation cover and an increase in open soil areas. The precipitation analysis showed that there is, especially in the Ruzizi plain, there's very low precipitation. There's very high precipitation for the mountain ranges. We also have this very strong changes from wet to dry season in the amount of precipitation. Then we identified the extreme precipitation events, which can be distributed throughout the study area, and they are not connected to a specific season, but there are some months where there is increased risk for extreme events. And I took a look at an IPCC report, and there it said that increase in November, December, and January precipitation is likely for the area, and at the same time a decrease of July precipitation, so during dry season, a further decrease in precipitation is likely. So it might be that in future we get even a larger number of these extreme events during some months, and also more droughts or drier July, which then leads to lower vegetation cover again. Then we combined these two factors, the vegetation and the precipitation, to an erosion risk index, and this is also again here shown on the right. We do get increased erosion risk for the Ruzizi plain, for the areas east of Lake Kivu and also especially north of Lake Kivu, and where the large cities of Bukavu and Goma are found. There is very low erosion risk for the forested areas, and these results aligned with the Russell simulation results. And as was just stressed by Felix and me a minute ago, it really is a nice result because we do get these strong similarities for the two approaches that have really two different methods used. So although there are some areas where the erosion risk is maybe a bit shifted, it's really satisfying results. Then we looked at the turbidity of Lake Kivu. Here we couldn't draw a quantitative connection on a larger scale and also on a longer time frame for the erosion risk that we identified and the turbidity of the lake. But when we take a closer look at river deltas or maybe other data sets that give us more information on the turbidity of the inflows of the lake, then we could maybe have a better validation of our erosion risk results. Then my colleague Xuyan just showed the urban growth in the area. So we looked at the two city agglomerations around Goma, which also covers cities in Rwanda, and the same in Bukavu, where we also looked at both sides of the border. And we saw that there was urban growth for the two cities from the year 1995 to 2005, especially in the city of Goma. There was a lot of city growth, which we could see from the world settlement footprint. And the Sleuth simulations show that there will be further city growth, especially around the city of Goma and especially on the Rwandan side along the infrastructure, so along the existing road network. This increase in city area will also increase the seal surfaces, so it will further increase the surface runoff, and with this may affect further the erosion directly. Also, the increase in city area might go along with an increase in population, and this would also increase, of course, the demand in space, but also in agricultural product, and could then further increase the pressure on soil erosion or on soils in general in the area. So this was the presentation of our results. We are now open for questions. I think there have been probably some in the chat already. So I hope we can have a discussion on our work now.
Thank you, Steffi and other DLR colleagues. I did want to flag, I think it would be helpful to give maybe a little summary of what's been discussed in the English chat so that our colleagues on the French chat can also see, because it's been quite dynamic. One question, I know that Atanas isn't here anymore from eCraft, was one of our partners receiving a grant with GIZ. I think we've talked generally about his question on the slope. I think what would be interesting that he brought up as a next step, and I think it would be very interesting for all of the participants to sort of identify where they see potential for next steps and how this research can be applied. And I think here what Atanas brought up that was interesting is taking the data like we talked about, combining it with the Russell model, and then looking at the district level, so looking at a higher resolution and integrating those slope classes, and that could help policymakers target certain technologies like progressive or radical terracing or other measures. So wanted to know if you had any thoughts on that question, since he was hoping that we could provide him a response in writing since he had to leave. If anyone is talking, you're muted.
So not sure if I got all points, but I see that the discussion on slope is still a crucial point, and as I mentioned, it's absolutely valid to have to consider the slope in general, but we don't want to illustrate or use the EO-based risk index as an alone standing index. That's not the aim we have with this analysis. It's really just to complement the existing erosion risk map based on the Russell model. So only in combination it makes sense. So I absolutely agree with the points are absolutely valid. So that's okay. That's the EO-based index we just presented is not an alone standing index. It's just useful in combination with the existing one that also uses then or integrate the slope. And in combination, I think that's the beauty of this analysis. We really can identify then the areas that are really prone to erosion. And I think, Christine, there was another point I just missed a bit. Maybe you can repeat that.
The question was, do you see from your research a potential to apply this at an even more localized level? So looking at the district level, for example, on the Rwandan side, that could actually potentially lead to some policy decisions about what sort of mitigation measures could be used to manage erosion.
Yeah. Yeah, we think that's possible. I actually do think that already what we have might contribute to this a bit, even though the resolution is a bit coarse on the first look. I think 0.25 degrees. The question was earlier, I was muted, is about close to equator, maybe 26, 27 kilometers or something like that. Depends always on the latitude. Already indicates in combination, and that's what Steffi also provided with the land use, already an indication if we have agriculture and the fields are managed in a way that the vegetation cover is very low when high precipitation is expected. We can identify this with the Earth observation, and then here some measures can be implemented in discussion with the local farmers. But that can be, of course, also this analysis can be also conducted in more detail by using other data. We had to use now this MODIS data because we have this temporal good coverage with a lot of scenes. So the chances are quite high that we have scenes with low cloud coverage, and to have this really this analysis on complete coverage without any holes. Given we would have a bit more time and to structure this analysis, we would be able to find solutions to work also with higher resolution data. So then there are several possibilities how we could structure this, using combination of Landsat and Sentinel-2, maybe even go downscaling from Sentinel-3 if necessary, but then we would have to see how the coverage is and the cloud coverage is, and how we can then engage in this. But of course, with this sensors, we could really go down on the smallest administrative levels and even on larger fields to identify these correlations or these aspects that we want to emphasize with this analysis. And again, this we can, of course, we can discuss if we, the next time, if you are more comfortable with having the slope directly in here. But again, I think it's a good solution to have the Russell model, the really physically based model on erosion risk, and combine it with the Earth observation data. If we have the possibility, if we have a separate analysis, we can combine the slope also directly. We did it on purpose not, because in this case we think it makes more sense. I hope that answered the question.
Yes. So I think at this time we can open up for questions. So if you have a question, you can type it now into the chat, or if you want to use the raise your hand function, which should be on the top right, so there's a little face with a hand, you can raise your hand and we'll call on you. This also goes for the French chat. The interpreters can let us know when there's a question, and they'll answer, or they'll ask it directly here to the DLR colleagues.
I see there's one more question in the chat, which relates to the turbidity data in the lake and the low correlation in this case with the erosion risk. I think Steffi tried to argue here because so I think the basic idea behind this, and that was more or less let's say something we really wanted to try in this case, if it works as a remote and assessment of the analysis, and more or less can you used as a validation. But it turned out that the products that are available from the Copernicus Land Service, they always cover several date range, and it is to have an automated analysis of the data, which allows also a quantification of the correlation, is quite difficult, because the direct date of the different scenes in the product that is provided by ESA is not obvious, and therefore we cannot really relate it to one single precipitation event. And to do this, we would have to try to have our own calculations, and that was not possible in the given time. And it is also not easy because, of course, after a strong precipitation event, the cloud coverage often remains. So we would have to wait always a bit until we have a cloud-free scene again. So that is still something that is used in other regions, other studies, and it would be very interesting to look deeper into this with additional data, with own analysis, and not be dependent on the ESA product. But in this case, we just were not able to process this product on turbidity on our own. For example, also with other data. For example, Sentinel-2 would have provided also an option to look deeper into this, and would be very interesting to look into this. Yeah, I hope that answers the question. If not, just raise your voice. And
yes, I agree with you, Felix. So we would have needed a higher temporal resolution, or we would need a product that is that covers the area directly after an erosion event, to see if we can really see an increase in turbidity in the river deltas, to connect the turbidity to the erosion. And that's difficult because if we have precipitation, then we have clouds, and then we don't have a product. So yeah, this is one reason why it's difficult. Sometimes you may get a turbidity information directly after the erosion event, but then you cannot do a quantitative analysis if you have 2 or 3 or 4 time points where you do get both information. But on the statistic analysis that we performed, it didn't turn out to really give supportive results here.
Thank you. I'm told we have a question on the French channel, so we'll let the interpreter convey to us that question now.
Yes, thank you so much for giving me the floor. So after your presentations, which were very good, thank you, and we accept that risks are really important with regards to these erosions in the different cities in Bukavu, Goma, and Chambubu, and also in the coast area in the Kivu Lake. But our concern is the following. We would like to understand how we can mitigate this type of risks, taking into account that in the Ruzizi plain, we really see very important erosions. And the area is quite virgin. And well, since you have not seen yourselves the area, maybe you cannot understand, but we really need to find solutions to mitigate that risk. You said that on the slope, that's where we observe more erosion risk. It's also true that the Bukavu city needs awareness raising programs or measures, because when you see the erosion there, and when you take into account other situations which are not good, and when you take into account also the slopes and also the other aspects linked to the city construction back in the 60s and 70s. So the city did not have the resources that it has now. So yes, now we have many new demands. So you showed those demographic demands also in terms of the Goma city. So yes, and when you take into account this erosion risk, that's very important. So we want to know what system could we implement in those areas to mitigate this type of erosion. If you can recommend something to us, we would like to understand whether there are some mitigating measures that we could use and implement to try and mitigate this risk. Thank you.
Yes, important question. Yeah, what can you do? I mean, we identified erosion risk, but what are the measures that you can undertake? So yeah, what I showed you was that of course that if there's no vegetation cover, the erosion risk is highly increased. And so one thing would be that we need vegetation cover as much as possible throughout the year, because also during dry season, when there is maybe not so much precipitation, erosion can take place. And we saw from the Ndvi that there is areas where we do have very low vegetation cover at this time of the year, and this will probably further increase with changes in the precipitation cover due to climate change. So one thing would be to maybe grow different crops that don't have this strong decrease in vegetation cover for the dry season, and to have year-round high vegetation cover, because this would hold the ground, the soil particles.
May I comment on this? So the objective of our study and the results we presented today, we are not on identifying mitigation adaptation measures. I know that's of course what in the end has to come out, and I also think Sam raised a question in the chat in parallel. Here it's, I think, and maybe I can combine the two questions. The next step would be then to combine the risk map of the Russell-based model and our results, and then to identify those areas that then are prone to erosion risk based on mainly on the topography in the Russell model, and also on low vegetation cover and high precipitation events that comes from our analysis. And for these areas, of course, it's hard to provide a general adaptation approach. One would have to look into detail, and that's not something we can do in this short-term project. So, of course, there are several standard measures, like Steffi already mentioned, but in some cases there are site specifications that has to be considered. I know that it's maybe not an satisfying answer from our side, but we did not look into existing measures. We would have analyzed what is already there. That's something we did not do in this analysis. So therefore, I'm not sure if we are with this study can really recommend specific actions on certain sites. But I think the next step, and that very much then relates to Sam's question, is to combine the two data sets, because that's what this study or our data processing really wanted to do, to complement the existing data set, the existing analysis. And with the combination of the existing Russell model and this, I think we can identify the areas at risk more detailed, and then develop for these sites adaptation measures. I think that's the next step to go. And depending on what then is identified, of course, one thing is then to develop the adaptation measures, or to apply adaptation measures. Maybe they directly can be identified, or to have a more in-depth analysis on the areas, because now we have a very large study area, but maybe it also can make sense to have a closer look with higher resoluted data on smaller areas to better understand the dynamics there. But that very much depends then on the analysis and the resources that are available, and the decisions for this has to be made somewhere else. Not sure if this is a satisfying answer again, but that's what we can say from the state of our analysis.
Following up, Felix and Steffi, on that, I know obviously it's, like you just mentioned, it's hard to provide any specific mitigation measures given the scale and type of data used here. But generally speaking, where would you see potential for, we've talked a little bit about it, but some specific ideas maybe for interesting follow-on work or further research? I think the erosion piece, like we talked about, would be one place, but if you have any other things that stood out for you where we could consider further research on, would be great to hear those recommendations.
Yeah.
So one thing that I would think would give us a bit more or better possibilities to really give estimations is a closer look at the specific land use in a higher resolution, so that we know what are really the land uses, so what kind of crops are growing, where there is increased erosion risk. And yeah, when we know that, then we can also maybe find croplands or agricultural fields that do not have this increased erosion risk due to low vegetation cover. So this could really give suggestions, really tell the people you can grow these crops that lead to a lower erosion risk during dry season or during precipitation events. So this would maybe be very interesting and very helpful also in the area.
Yeah, I agree. That's one way to go, and also, of course, the land management itself. So which crops are planted, when do you harvest the crops, and how do we align it with the now identified maximum precipitation events? I know that's still on the CHIRPS data, but I think for the risk model, it's a totally fine data set. Because in the end, it doesn't matter if CHIRPS is a bit off. I know it underestimates sometimes a bit, but that's not important for a year, because we just have to identify the general date of these events. And as Steffi mentioned, the IPCC report also expects a change in the regime of the precipitation events, of the maximum events. And here, that's something that has to be considered. So I think that's really important, and better land use data, especially on the farmland, would be extremely valuable to identify better this combination of, or the time constraints between the land management and these events that really trigger the soil erosion, and that really would probably provide the option to get into discussion with the local farmer associations and local farmers themselves to identify here adaptation and mitigation approaches. I think that's the way to go, besides from combining, I mentioned it already, combining these two analyses, which is I think the next step to go itself. But yeah, I think there are many options. But I know it's a lot of work, and yeah, I think that's what we could suggest from this point.
We have a question on the French channel. I know Charles has a question, and so does Hendrik. Charles is in the room with me. I'm looking at him. You need to.
Hello.
So his is in the
morning.
chat. Do we can maybe have the.
Sorry, I have followed with great interest the results of what has been done on the ground. I would like to say that the studies that we are carrying out in the Lake Kivu Basin and Kivu River should help us to find some solutions concerning the diversity in our basin. Concerning that, you have all identified that the topography, of course, and the human activities are at the start of erosion risks. And the degradation of the environment is more caused by the presence of humans. I would like to say, or to know, which consequences are caused by demographic growth in our basin compared to, well, for the different ecosystems. if there is demographic growth, are there more risk of erosions? Because, as I would say, there is demographic growth in Bukavu, in Goma. There are houses that are stratified. There are a lot of risks and loss of human lives, degradation of environment. And these risks of erosion are going to increase in the forthcoming years. So this is going to help us identify these risks and the incidence of demographic growth compared to the erosion risk that will increase in the coming years. So this should help us prevent things because as the climate change increases, this demographic growth will have even greater effects than the ones that we are witnessing today. So the study should say something about the incidence of erosion risk on the biodiversity we find in the basin. Some crops are destroyed because of erosion. When we identify this, this helps us. The study cannot limit itself to observation. It should lead to adaptation measures and prevention also. This is going to help us. Otherwise, our capacity to give solutions to our problems around the basin, well, this is what I wanted to comment upon concerning this study. Thank you.
Yeah, thank you very much for your comments, valuable comments, and I totally agree. What your analysis of the situation and drivers of erosion from human activity to urban growth to different also land management systems that are equally important as climate change. And I think here are many drivers that influence the situation and that have to be identified, also the interrelations between them. That was not completely the objective of this study. So we focused on what we presented, but I totally agree with especially the demographic growth that of course increases the pressure on the land itself, but also on the settlement growth, and thereby also of course on the vegetation in general that holds the soil. So I think that there are well-known interrelations, and with the data we provided, that we had, at least the objectives of this study were identified in discussion beginning of the project with colleagues from Rwanda and GIZ. We at least try to support the understanding of these systems as well as the urban system, the growth system. So Xiang here provided the urban growth modeling on a state-of-the-art model, not state-of-the-art, sorry, business as usual model, which assumes growth that is extrapolated from the past developments. But of course, he can also be included some scenarios to adapt this growth with different assumptions, basic assumptions. And that would also influence the results. But I think this business as usual model already indicates quite well where we can expect. In most cases, it's also well known. I know you're the experts on the ground, you know where the areas are where the urban growth takes place, but with these models, at least we can quite well delineate the areas on a large scale, and I think therefore it's a quite valuable input. And yeah, as we mentioned, it would be, of course, now from what we have from this study, but also what has been done in the past. I think this report that is provided by Abakir is valuable, and really I read through it, and it took a lot of effort. I can't imagine how much effort it took to do this report and all the analysis inside the data collection. I think with this is a great base to further analysis, but also directly to use this wealth of data and information to develop strategies, mitigation adaptation strategies, and then to support the decision makers to find and implement solutions. We can only contribute with this study a bit to this, but of course we are eager always to work on this in this area, because that's this is not a topic that's just important in Rwanda, in Congo, in this area. As you might have known, that's the same here also in Germany. So we are always focusing on this topic. Last year we had devastating floods with extreme erosion in Western Germany, in Central Europe, and we're focusing on these topics a lot. We try also to find this mitigation and adaptation measures here. Of course, they are a bit different because we have different land management, but I think with this additional information provided by the modern satellite systems, at least we can contribute to the understanding, and with this understanding, better mitigation measures can be developed. That's at least what we expect and what we learned from in the past, and we hope that with this analysis we provide and the data we provide, and Steffi, maybe you can paste the link with the data sets also in the chat. I forgot this in the beginning. I didn't find the link. You have it. So with this data that then also can support this decision-making processes. And yeah, this is just a study that complements to this overall process that is necessary. Therefore, I totally agree that it might not be completely satisfying, because we are not able to provide the one solution, and that's also not the objective of this study. That's important to say, but for us it's a very important topic, and we are happy to contribute also in the future.
Thank you, Felix and Stephanie. I'll read a question now that is from Charles Hekisinana from the French chat. So his question was around understanding better what you think might be the drivers behind the high erosion risk in the Ruzizi plain, noting, of course, that there is very low slopes. I mean, it's a plain, it's flat, and so he wanted to have a little bit of clarification on why you think that there might be such high erosion down there.
Yeah, right. That's a good question, and I think this contributes then probably also to again to understanding of this erosion risk index provided. So the Earth observation based index we provide focuses on the vegetation cover and the precipitation intensity. So those two are the factors that influence the erosion in this case. And we did not integrate the slope on purpose, as I mentioned before, because it's already used in the Russell model. So therefore, the Earth observation-based erosion risk index cannot be seen alone standing. It has to be seen in combination. But anyhow, the general assumption is that with a low vegetation cover and very high precipitation events, there is erosion caused. Of course, the higher the slope, the higher the result of this event. And therefore, the combination with the Russell model is important. But from different soil inventories studies on erosion, we know that even on a quite stable slope or low slope area, the erosion already can take place, but of course the transport of the soluted sediments is not that strong and that far. Here is just the risk of erosion and not what it's not a quantification of the amount like one can estimate with the Russell model. So therefore, again, we very much want to promote to combine these two analyses to identify those areas which then are indicated with extremely high risk of erosion. And I think it would be, and that's something unfortunately we could not do in this project, and also to really have a closer look at those sites on the ground, and then also to validate what was identified by the Russell model and also the Earth observation index, and then better understand which of both models maybe contribute more or less, and where we have to do some adaptations in one or both models, because they're of course both not perfect, and we miss a bit the ground information on our side for this analysis. Would be great to work further on this and add all this information. I think that here the potential is quite large to improve, but solely from the remote sensing data that is available, I think Steffi did here a great job in analyzing all this data, and it's a first indicator. And now the next steps and decisions has to be taken. And if there are any further questions, of course, we gladly support this integration of the two data sets. And also, if there is still some clarification needed for some of the data sets that are provided, that's we do not stop with this presentation here. Of course, we're always available. So we hoped, or we hope that we with this data sets, we have the first step to take action further.
Great. There was a question in the English chat that I'll just read aloud. It's from Jean d'Amour. The question is it possible to use erosion risk in areas with mining activities? And if so, do they go through the same procedures while processing the data? And what assumptions might they need to consider?
Yeah, I like this question very much because it opens another perspective. And yes, we can in general use the data already available, but if you go to mining areas, I would focus on more high resoluted data to be able to provide more detailed information of the vegetation loss in these areas. And then this might even provide more options than with also the turbidity data as a reference, since we are not dependent that much on the precipitation events or strong precipitation events, since for mining areas the erosion risk is in most cases much higher, since the human impact here is extremely strong, and therefore this is I think quite a valid approach to go with the vegetation cover in general, but here with more high resolution data. But Steffi, maybe you can also give your opinion here. You'd work on this data more than I did.
Yeah, sure. So of course we can use this approach for any surface land use type, also for mining, because we just look at the vegetation, which will be probably low for mining areas and then lead to an increased erosion risk. But so the mines itself, they will be better analyzed with higher resolution data to get really better, more accurate results. Because here in this analysis is quite generalized and tries to cover a large area with large different kinds of land use. Yeah, but in general, I would say it's nothing speaks against this, using this for all types of land use and also for mining activities.
We just have a few minutes left, so if there are any remaining questions from the English or French channel, go ahead and raise your hand. One point while we're waiting for one last question that was discussed on the English channel between something that Patrick Bracken raised, which I think is interesting to talk about, is the question of whether it might be more interesting to analyze turbidity in the tributaries and rivers along the plain, but also within Kivu. The potentially perhaps the lake isn't necessarily the place to look for this erosion turbidity relationship, but perhaps it is amongst the rivers and tributaries. So wanted to know, DLR, if you had any responses or thoughts about that observation.
Mm-hmm. Yeah, so I would agree absolutely that in the rivers you will see a lot more signal of erosion. But of course, this is a bit difficult to do with a satellite that has a resolution of 300 meters. So this is very unfortunate, and there are somehow the borders of use of satellite data. Yeah, you would need measured data from the rivers. This would be the best thing to do. And I found studies that did something in that way, that measured the particles in rivers in the eastern area of Lake Kivu. Yeah, but this is of course higher. I mean, you need more time, more effort, more money as well to do these kinds of measurements. But they would give much more reliable results, of course. I mean, we try to decrease the spatial scale for the turbidity by using only the coasts of Lake Kivu and the turbidity along the coasts, but that was even too generalized to get these satisfying results here.
Yeah, and I also try to answer this question in the chat, so it's a very interesting question, and I very much like the approach, since some colleagues are doing this for the Rhine River here in Germany, for example, for operational monitoring of the sediment transport in the river. So they have the ground measurements on one side, but they use Sentinel-2 data actually to identify the sediment load of the river. And this is so it's feasible to do this, and it's a very interesting approach, because then it's also possible to combine this with different precipitation events and so on. But the same here, if you have a very strong precipitation event, often the cloud coverage remains a bit longer, and it's not always then that easy to relate a strong precipitation event to the sediment in the river. But anyhow, I think that's also interesting to look in. But it's to use Sentinel-2 data here for the entire catchment, it will require enormous processing effort. So that was, of course, not possible within this project, but in general, that would be interesting. Maybe also only for a smaller catchment to learn about it, and if it's possible with the cloud coverage that is to be expected in the basin. And what we did not discuss today that much, and we did not receive during the project, or we did not have access to the project, it's better to say that way, we did not have any measurement data. As far as I understood, there are some, but we at least could not combine our data with this measurement data, which would of course also have been helpful, even though it's only a few point information from these measurements. But that can be maybe afterwards also be combined with the data sets we provide. So if you have access to this data, of course, that would be also an interesting approach to go.
Thank you. I know we're at the 12 o'clock mark. We still have a couple questions. So what I suggest, since we don't take up too much of your time, DLR, is we have one last question on the French channel from Ndvi. And then from there, the rest of the questions can be sent in writing, and you can discuss via email. So we'll leave the floor now to Jeremy.
Thank you for giving me the floor. I'm sorry because I joined late. I did not have a good connection, but I studied the documents that you sent and I had several questions. But actually, I would like to say that I followed the different contributions by my colleagues and I understood that they have the same concerns as mine, but I just wanted to ask you whether you can please send this presentation to us so that we can have it. And so that if we have further questions, we will be able to send them afterwards to you. Thank you.
Yes, absolutely, we can. I think the presentation was actually shared yesterday already or 2 days ago by Steffi or by Christine. So maybe it can be sent again. And additionally to the presentation, I also shared a link where you can download the data package. So this is really the remote sensing data or intermediate products. And there's also a short description within this folder where you can download the data and take a look yourself if you want. Maybe this can also be shared via email. Or yeah, or at least maybe you can share the link in the French channel.
Yeah, Steffi, maybe you can give also a brief warning that it's a quite large data package.
Yes. Yeah, actually, it's not as large as I was thinking. But yeah, it's I think it's 2 GB or so. Yeah.
Yeah, so you would need a stable internet connection to download the 2 GB package.
Yeah, and it's geodata, so you can look at it in QGIS, for example, or your GIS system. This would be best.
Great. We just have one last question in the room here.
Mm-hmm.
And then I think we can conclude. So Venon?
Just a small concern. I wanted to know how those last files used to use those maps, how will be shared, possible, so that you can integrate with our existing data set in order to plan, to do, or for our catchment management plan. So we wanted to know how those last files will be shared.
Sorry, I didn't understand. I didn't have a good connection, I think.
Is the question about, so this link in the chat contains all of the raw data.
Yeah, not all of the raw data.
Can you explain a little bit more, Steph? I think the question is about can you explain a little bit more about the data in the link and how it can or cannot be manipulated? For example, for Rwandan Water Board, they're doing catchment management plans, and so this could be some data they can integrate into that work. So maybe just a little extra info on your advice for what's in there and manipulating it.
Okay, so it's not the raw data that I downloaded because this wouldn't be necessary. You could download it yourself. It's open source data. That's the basis. Yeah, there's, for example, the aggregated data in the hexagonal grid. included for the vegetation and the precipitation. There are the seasonal means of vegetation, for example. Yeah, what else? Yeah, you can just take a look. But it's really a large amount of files. And there's also a short description included into this directory, and also the report where it's explained how this data was manipulated. But you can always, of course, contact me as well, and we can take a look at the data together and then see what you can do with the data and how you can use the data. But you would, of course, to do anything with the data, you would need a GIS system to open it, for example, to like a QGIS or yeah. You cannot just open it with a Windows image reader or so.
Okay, thank you. I know there's still some questions left, but we've gone over our time. So what I'd like to suggest is, as DLR mentioned, they're open to, continue discussion or clarifications. So if you have remaining questions, please email them to Stephanie Bilgram. She's the GIZ colleague who sent you the calendar invitation and emails. In the emails from her, you'll already find the report in English and French, as well as the PowerPoint. I know maybe some of you, Patrick mentioned that he had an issue opening the French version, so we'll double check that everything is okay. But send your questions to Stephanie Bilgram via email. You can just reply to her from the invitation. She will collect the questions and send to DLR. And then I believe in your contact info, Felix and Steffi, it's in this PowerPoint, I think, somewhere.
There's actually, I think, no email address, but we are also in the email that Stephanie Bilgram sent around. So.
So when we send out, we'll send out a closing summary email. We'll reattach the PowerPoints, the report in both languages, as well as the download link. And we'll include in that email the DLR colleagues' emails. But in the meantime, you can already send questions to Steffi, who can transmit them directly as one to DLR, which will make it easier for them to answer all the remaining questions from this discussion.
Okay. Yes.
Great. Okay. Well, so with that, I'd like to thank DLR for their great work. I think it has posed just as many questions as answers, which is the show of the good research done. There's a lot of potential for next steps and further research. And I think that this is one of the first times we've had such a analysis done on the basin level in a uniform way, taking advantage of all of the rich open source remote sensing data. So of course, like we mentioned, this data is open to everybody, the report and the data download that DLR sent. So if you have colleagues who couldn't make it today, you just let us know and we can send them the information, or you can. And as a reminder, this session is also recorded, the French and English. So you can refer back to this and you can also send it around. And when we have the recordings uploaded, we'll send you that link as well.
Okay, yeah, thank you. Thank you also from our side. I think it was really great to perform this this research. It was really interesting project, I think, despite the short time frame and the short time that we have had. But I think it shows that there is a lot more that we can analyze, and yeah, maybe in the future we can discuss on further projects in this direction. We will see. And also thank you for your interest today and these many questions. And yeah, I'm looking forward to answer more of your questions together with my colleagues via email. So feel free to ask if there are any urgent questions.
Great.
Yeah, also from my side, thank you very much for this fruitful discussion today. I think that's always good to have this exchange, and therefore it opens always a new perspective, and that helps us too.
Great. Okay, thank you, everybody. Have a great rest of your day, and we will stay in touch and get the rest of your questions answered via email.
Yeah, thank you. You too. Have a great day.
Okay,
Bye.
thank you. Thank you.
Thank you. Bye.
Yeah.
Well, Cozy, goodbye.
Bye.
Thank you so much.
Bye.